Right, so multiple choice questions on progressive and stationary waves. Question 1, it says 2 points on a progressive wave are 1/8 of a wavelength apart. The distance between them is 0.5 meters and the frequency of oscillation is 10 hertz. What is the minimum speed of the wave? So we're told that, so we have a wave, so that's a full wave, that's one wavelength. That's half, so that's quarter, that's 1/8. And we're told that there's 2 points in the wave and the distance between those points is 0.5 meters. So the distance is equal to 0.5 meters, and that's equal to 1/8 of a wavelength. Therefore, the wavelength is equal to 4 meters. The frequency is 10 hertz. What's the minimum speed of the wave? The speed of the wave is given by frequency times wavelength. So that gives us 10 multiplied by 4. So that's 40 meters per second. So it's answer D, 40 meters per second. Question 2, which of the following waves cannot be polarized? And when they see this sort of question, only transverse waves can be polarized. Therefore, which of the following waves cannot be polarized? That's the same as saying which wave is longitudinal. So that's going to be some form of sound wave, and the only one of those, it's not radio, it's not microwave, it's not ultraviolet, which are all EM waves, so it's ultrasonic is the answer. Answer B. Question 3, which of the following is correct for a stationary wave? So a stationary wave, it has nodes and antinodes. At the nodes, the amplitude is 0. At the antinodes, the amplitude is maximum. So between the two nodes, the amplitude of the wave is constant. Well, that's not true, because the amplitude at this point is different to the amplitude at this point. So that's definitely not true. The two waves producing a stationary wave must always be 180 degrees out of phase. Well, that's not true, because the two waves are moving past each other. The separation of the nodes for the second harmonic is double the separation of the nodes for the first harmonic. So first harmonic looks like this. Second harmonic is like this. So we have node, 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 and node. So if that's the distance L, separation between the two nodes in the first harmonic is this distance L. Separation between the nodes in the second harmonic is half of L. So this is not true, because it's saying it's double. The separation for the second harmonic is double, where it's actually half. Between all nodes, all parts of the wave vibrate in phase. This is true. What that means is all of these parts of the wave are all going to be moving down together, while all of these parts of the wave will be moving up together. So they're all in phase, they're all synchronized. So the answer is D. Now, question 4. Sound waves cross a boundary between two media, X and Y. The frequency of the waves in first medium is 400 hertz. The speed of the wave is 330 meters per second. And the speed of the waves in the second medium is 1320. What are the correct frequency and wavelength? Okay. So when we have a wave, it's crossing a boundary, and we've seen this with refraction, for example. What we see is that going from one medium to another, the speed changes of the wave, so the wavelength changes. But it's important to realize the frequency doesn't change. For the frequency to change, what we would be saying is that we've got more waves per second or less waves per second, simply by the fact that something is passing from one medium to another. So this would be like air as it light as it travels through air, and then it travels, meets the boundary with a window, and it travels through the window, somehow extra waves are added in just by the simple fact that the light was traveling through glass. This would essentially mean adding energy, because remember, the waves are being generated by some sort of oscillation, and we'd be trying to add energy if we were adding in extra waves, or we'd be taking energy away if we were removing waves, and that's against the principle of energy conservation. The other way you can think of this is, and the analogy I like to use here is the idea of when cars are on a motorway and all the lanes are open, they're traveling very quickly. If some of the lanes close, the cars then start to slow down, and what you see is the cars bunch up together. The wavelength, the distance between the cars decreases, but we don't suddenly get extra cars suddenly popping into existence in the middle of the traffic, just simply because a lane has been closed. So we're told that the frequency of the wave is 400 Hertz in X, so it has to be 400 Hertz in Y. So the answer is not going to be A and it's not going to be D. It's going to be one of these two. And we're told then that the wavelength changes. So remember, the speed is equal to frequency times wavelength. If the speed goes up, frequency can't change, so the wavelength must increase. So to increase the speed, I have to increase the wavelength. So as the speed has increased in Y, that means that the wavelength must have increased. And the only one that this is not B, it has to be C. What you could do to be sure, if you had time, is to say, well, speed is equal to frequency times wavelength, so I can use wavelength equals speed divided by frequency to give me the wavelength at the start, which is 330 divided by 400. And then the speed of the waves afterwards, the new wavelength, is 1320 divided by 400. And then I can get the ratio of those. I can work out what that wavelength is from that equation. Check that's the right answer. Okay, question 5, showing two pulses on a string traveling towards each other. Which of the following diagrams shows the shape of the string when the pulses have passed through each other? Now, when pulses superpose, if we assume that there are no losses due to friction, for example, if this was a piece of string, the waves will then just continue on carrying their energy. When they meet, they superpose, so the overall effect comes from adding together the displacements of each of the individual waves, but there is no effect on the actual pulse itself. So it can't be this one, because this one shows the pulses have disappeared, which will happen when the two pulses, one is above and the other one is below. Then yes, at that moment we will get destructive interference, but then a fraction of a second later the pulses will have passed through each other like that. So it can't be this one. It can't be this one because the one that was at the top is moving from left to right, so it must be over on this side. I'm going to jump down to D. It can't be this one because this is saying that the shape has changed. The shape of the pulse has changed. So the only one it can be is C. Right, question 6. Which one of the following provides direct experimental evidence, that light is a transverse wave motion rather than a longitudinal wave motion? So two light waves that are coherent can be made to interfere. This is not true. This can happen, but it can also happen for sound. So because that can happen with both transverse and longitudinal waves, that won't be sufficient to give us evidence that light is transverse. Light can be diffracted, that is, it can spread round obstacles, or it spreads out as it goes through small gaps. This is also true with sound, so it can't be that one. The number D, the intensity of light from a point source falls off inversely. This is also true of sound, because if you imagine, if this is the source of my wave, the wave, whether it's light or sound, will spread out in all directions. And as it gets further and further away, you can see that the energy being carried by the wave is being spread out over the area of this large sphere. So it's been spread out over the area which is proportional to the distance squared. So this is true whether that wave is light or sound. So this means for the only one that this can be true for is polarized, because polarized means that the wave is only in one direction, for example like this. So it's at an angle like this. This can only be true, it's the oscillation is happening in one plane, which is only true for transverse waves. So the answer here is C. Question 7. The sound quality of a portable radio is improved by adjusting the orientation of the aerial. Which statement is a correct explanation of this improvement? The radio waves from the transmitter are polarized. This is true. This is because what's happening inside the antenna is that through an electric alternating current, the electrons are being oscillated, moving in one direction and then moving in the other direction. And that's what's generating then my radio wave. However, so that means that the radio waves coming from the transmitter are polarized. This is also true, for example, of microwaves. So when we generate microwaves, they are already polarized. So this means that statement B is not true. And then the radio waves become polarized as a result of adjusting the aerial, or unpolarized as a result of adjusting the aerial. These are both untrue, because no matter what orientation we put the aerial in, the radio waves are going to be generated in one plane. Only they are polarized. So the answer here is A. Question 8. We have a microwave transmitter being used to direct microwaves of wavelength 30 millimeters along a line XY. A metal plate is positioned at right angles to XY with its midpoint on the line shown. When a direct detector is moved gradually along XY, its reading alternates between maxima and minima. So which one of the following statements is not correct? So let's think about what's going to happen here. So the transmitter is generating a wave. The wave is moving down in this direction. It's going to hit this metal plate and it's going to reflect back. So what we're going to get here is happening is a stationary wave. So we're going to get a stationary wave produced. The stationary wave, remember, it's made up of nodes and antinodes. And we're told that the wavelength is 30 millimeters. Now, the maximum signal we're going to get at the antinodes and the minimum signal at the nodes. So the distance between the minima will be 15 millimeters. Distance between the maximum will be 15 millimeters. And the distance between a minimum and maximum will be half of that, 7.5 millimeters. So let's see what options we've been given. Now remember, we're looking for the one that's not correct. Distance between two minima could be 15 millimeters. Yep, that's true. The distance between two maxima could be 30 millimeters. Well, between the two adjacent ones, it's 15. But if we take the next one along, that's going to be 30. So this one could also be true. If I look at the last one, the distance between a minimum and maximum could be 37.5. Well, between this first maximum and this third maximum, that was 30 millimeters. And then another 7.5 millimeters, we've got a node. That gives me a total of 37.5 millimeters between this antinode and this node. So this one could be true, but this one is false. So the answer, the false statement, is C. Then we've got, by approximately how many times is the wavelength of audible sound waves greater than the wavelength of light waves? So we have light if we think about speed, the speed of light is 3 by 10 to the 8 meters per second. And if you didn't remember that, it's given in our data constant sheet here as the first one in the data constant sheet, is the speed of light. The speed of a sound wave is roughly 300 meters per second, or that's 3 by 10 to the 2. Now note, I've rounded that to one significant figure because we're looking at approximately here, and when I look at the answers, it gives me in powers of 10. So I'm only really interested in comparing these in terms of powers of 10. So speed of sound is 3 by 10 to the power of 2. Speed of light is 3 by 10 to the power of 8. And I want to know how many times is the wavelength of sound greater than the wavelength of light waves. So what's the wavelength going to be about? Well, the wavelength, so it's speed divided by frequency. The frequency of visible light is something around about 4 to 700 trillion hertz. So let's just say in the center something like, let's write it as 3 of the same, 3 by 10 to the 14. So that gives me that the wavelength of light that I'm expecting to get is going to be something of the order of 10 to the power of minus 8 minus 14. So that's 6, 10 to the power of minus 6. The wavelength of sound, so it's speed divided by frequency, it's 3 by 10 to the 2 divided by, and here we're looking at something around about, say, meters, tens of meters. So we can say it's around about 10 to the 2. So that's going to give us, so 10 to the 1, I should have said 10. So that going to give us an answer of around about 10 to the 1 meters. To give us a difference between these two of the wavelength of sound is around about 10 to the 7 times larger. Now, which one of these is going to be? The closest one we have is B for 10 to the 6. Now, it's quite hard to remember some of these numbers, and one of the things about light in electromagnetic waves is they're nearly always quoted in terms of wavelengths. So you'll be shown pictures like this showing the electromagnetic spectrum. In this case, this is a picture showing the effect of atmosphere and electromagnetic spectrum, and it's shown in terms of wavelength. And when they have pictures of the electromagnetic spectrum in textbooks like this, they generally speaking show this in terms of wavelengths. So it's probably easiest in this sort of question just to remember some key figures. So basically we can say that visible light is around about from 400 to 700 nanometers, something like that, and red light around about 600 nanometers. So nanometers is 10 to the minus 9, so that gives me, this is around about 6 by 10 to the minus 7 meters. That's the typical wavelength of light. It's in hundreds of nanometers, or 10 to the minus 7. Sound, its wavelength is in meters, typically. We know this because a doorway is roughly a meter wide, and sound can diffract through a doorway, it can spread out because its wavelength is similar to the width of a door. So for this question, we could do it by remembering what frequencies are and then using the equation for velocity equals frequency times wavelength. But the easiest thing to do, and the one that's most widely quoted are the wavelengths for electromagnetic waves. And again, this would give us something that the sound waves would be around about 10 to the power of 7 times larger. So the closest one is B, which is 10 to the power of 6. Right, so next question, question 10. A stationary wave is formed by two identical waves of frequency 300 Hertz. They're traveling in opposite directions. So these are coherent, they've got the same frequency. If the distance between adjacent nodes is 0.6 meters, what is the speed of each wave? So what they're saying is, here's my stationary wave, node, 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 antinode, antinode. So the distance between the nodes is a half of a wavelength, and they tell us that that is 0.6 meters. So the wavelength is equal to 1.2 meters. They've told us the frequency. The frequency is 300 Hertz. What's the speed? So we use speed is equal to frequency times wavelength. And if we put those numbers in, so we've got 1.2 multiplied by 300 to give us an answer of 360 meters per second, or C. Right, question 11. This is quite a popular type of question. You often ask it either with something like this, wave moving along a string, or waves moving along the sea. And what they want, the reason why they are asking this question is they want to see if you can distinguish between the oscillations that are happening on a particular point compared to the movement of the wave along the medium. So it's a snapshot of a wave, so that's distance from left to right. This is one point in time. And they're saying at the instance shown, point P is at the maximum displacement and point Q is at the zero displacement. So this wave is going to move this direction. So the maximum is going to move in this direction. What that means is the point that was here, a moment later, it's going to move up to where P was. This point is going to then move up a little bit, and all these points are going to move up. So in order to work out what's going to happen to a particular particle, when the wave's moving in that direction, we look to the left and see what's going to happen. We see what the wave looks like. So here we'd see that the wave looks like this. So the point P, as the wave moves this way, it's going to move down all the way until it reaches the maximum negative displacement. So P, it's going to be one of these two, C or D. The point Q, again, we'll look to the left. What's going to happen? Well, it's going to start by going up, and then it's going to go down. So it's going to be rises and then falls, which is this one, which means that the answer for this question is D. This is a really popular type of multiple choice question. It comes up quite often. Speed of sound in water is 1,500 meters per second. For a sound wave in water having a frequency of 2,500 Hertz, what is the minimum distance between 2 points at which the vibrations are pi/3 radians out of phase? Okay, so we're looking for a distance between 2 points. So we have to relate the distance between 2 points to the phase difference. So what does that mean? Remember, the phase is saying where we are on the wave. So that's 0, that's pi/2, that's pi, 3 pi/2, and that's 2 pi. And we're told that they're pi/3 radians apart. So that's pi/2, distance apart. And so we're looking, that's 2 pi. So we're looking for a distance that between this point and this point, we're saying that's pi/3. So the question we're asking ourselves is, how much of the wave cycle is a phase difference of pi/3? So one wavelength is equal to a phase difference of 2 pi from this point to this point. So therefore we have 1 radian is going to be 1/2 pi wavelengths. therefore pi over 3 is going radians is going to be pi over 3 divided by 2 pi. So that gives us a sixth of the wavelength. So we're looking for the distance between these, and we can see that if we can get the wavelength, we can work out what that distance is. So what are we told? We're told that the speed is 1500 meters per second. We're told that the frequency is 2,500 hertz. We know that speed is equal to frequency times wavelength, which gives me wavelength is equal to speed divided by frequency. So wavelength is equal to 1,500 divided by 2,500. So the value we get for the wavelength is 0.60 meters. So it's 1500 divided by 2500, so that's 0.6. And we know that we're looking for the distance between the points, which is a sixth of that. So it's 0.60 divided by 6, which gives me 0.10 meters, or the answer B. Okay, so next question is question 13. Which of the following properties of light waves do polarizing sunglasses depend on for their action? Now, one of the reasons why people buy polarizing sunglasses, they're typically bought by people who, for driving, or often for when it's sunny, and it's particularly bought by people who are doing water sports, and especially things like fishing. Why? Because what happens is light, when it reflects from water or a surface, is coming in unpolarized from the sun, and it leaves the reflected light is polarized in one plane. So if we can have then a polarizer which only lets through horizontal components, or components that are in a plane that is at 90 degrees to the plane of the polarized light, then we can remove this reflection. And if we're looking trying to see an object inside the water which is also producing light, then this, by removing the reflected light, the glare, we're able to see objects more clearly. So what do polarizing sunglasses depend on? It's clearly not interference. It is to do with polarization. It's not to do with things happening inside the eye. It's to do with the light being polarized as it's reflected from the surface. So the answer is C. Question 14. Which line A to D in the table shows the correct relationships for the respective wavelengths and frequencies of light waves and sound waves? Well, we already had a very similar question before. We know that the wavelength of sound is very much larger than the wavelength of light, in the order of 10 to the 6 to 10 to the 7 times larger. And we know that the frequency of light is very much larger than the frequency of sound. So sound waves in hertz, or tens or hundreds of hertz, or maybe thousands of hertz, whereas light is in frequencies of trillions of hertz. So in terms of these, we have the first thing for the wavelength is we should have the sound wave is very much larger than the light wave. So it's not these. And for the frequency, that the light's frequency is very much larger than the sound, so it's not that one, which just leaves this one. So the answer is A. Okay, next question, question 15. We have, right, question 15. 2 points on a progressive wave differ in phase by 1/4 of a wavelength. The distance between these points is 0.5 meter. Frequency is 10 hertz. What's the minimum speed of the wave? So we know we're going to use this equation. Speed is equal to frequency times wavelength. We have the frequency, so we need to know what the wavelength is. We're told that the 2 points have, the phase difference is pi over 4 radians. That corresponds to, well, 2 pi radians is 1 wavelength, and for 1 radian is 1 over 2 pi wavelengths. So pi over 4 radians is going to be pi over 4 times 1 over 2 pi, which is 1/8 of a wavelength. So the distance between the points is 1/8 of the wavelength. So the wavelength is equal to 8 times 0.5, which is equal to 4 meters. So the speed is then 10 multiplied by 4, 40 meters per second. Answer D. Next question. We have question 16. Which line A to D in the table gives a correct difference between a progressive wave and a stationary wave? So we have, in a progressive wave, all the particles vibrate. This is true. In a stationary wave, some of the particles do not vibrate. So in a stationary wave, we have nodes and antinodes. And at a node, the amplitude is 0. So the particle doesn't move. In a progressive wave, which is moving, for example, in this direction, this part of the wave, some split second later, the wave is going to be here. So that particle has moved down, this one has moved up, and so on. So all the particles will end up vibrating. So this is true. So we could stop there, we found the answer. We can just double check the rest of them. None of the particles vibrate with the same amplitude. So in a progressive wave, it's always the same amplitude. Remember, the amplitude is simply the maximum displacement for a particle. So all of the particles are going to end up eventually reaching the maximum displacement on this side and then going down to the maximum displacement on this side. So they all have the same amplitude. This is not the case in the stationary wave. The stationary wave, the amplitude at the node is 0, whereas the amplitude at the antinode is very large and it has different amplitudes in between. So none of the particles vibrate with the same amplitude. This is definitely false. And this is all the particles vibrate with the same amplitude. That's also false for a stationary wave. Here we have progressive waves. All the particles vibrate in phase with each other. Well, this is clearly not true. For example, this point is coming down. This point is going up at the next point in time. So these points are not in sync. So this is not true. None of the particles vibrate in phase with each other. That's also not true. So all of the particles here will all move down together, while all of these ones between these two nodes will all move up together. So they're in sync. They're in phase. So that's also not true. And finally, progressive waves. Some of the particles do not vibrate. That's not true. That's for a stationary wave. And stationary wave, all the particles vibrate in phase with each other. That's not true. So all of these particles are in phase with each other, but they are out of phase with the particles between the next two sets of nodes. So that's not true. So the answer is A. Question 17. Stationary waves are set up on a length of rope fixed at both ends. Which of the following statements is true? So we have, again, our stationary wave fixed at both ends. We've got nodes. We've got antinodes. And it says, between adjacent nodes, particles of the rope vibrate in phase with each other. This is true. So for example, if all of these, the rope is up here, all of these parts of the rope will move down at the same time as all of this part of the rope will move up. So this is true. The midpoint of the rope is always stationary. That might be true for second harmonic, but it's not true for the third harmonic, which we can see there. The midpoint here is an antinode, so that's definitely false. Nodes need not necessarily be present at each end of the rope. Each end of the rope is fixed, so the nodes are definitely there are definitely nodes at each end. Particles of the rope at adjacent antinode always move in the same direction. So that they're saying here is the particles that are here will move in the same direction as the particles that are here. And we clearly see that's false. That when this one moves down, this one moves up. So the answer for 17 is A. Question 18. A wave of frequency 5 Hertz. Its speed is 8 kilometers per second. So that's 8 by 10 to the 3 meters per second. Moves through a medium. What is the phase difference in radian between 2 points 2 kilometers apart? So what we first of all need to work out is what is the wavelength. Wavelength is equal to speed divided by frequency. So that gives me the wavelength is equal to 8 times 10 to the 3 divided by 5. So the wavelength is equal to 1.6 by 10 to the 3 meters. Now, we're looking for the phase difference in radians between 2 points that are 2 kilometers apart. So what that's saying is that one wave is 1.6 kilometers. And we're looking for points that are, so then we've got another 0.4 kilometers. We've got the point we're looking for. Now, 0.4 is a quarter of this wavelength. So we're going to move 1/4, and 1/4 means it would be back up at the maximum again. So here we've got 1 1/4 wavelengths. So what is the phase difference between those 2 points? Well, the phase difference is going to be, remember when we reach 2 pi, we start again at 0, we're up at the maximum, so the answer is going to be pi over 2. Answer B. Question 19. Source emits light of wavelength 600 nanometers. And remember, nanometers is 10 to the minus 9, so that gives me 6 by 10 to the 7, minus 7, I beg your pardon, meters. As a train of wave lasting 0.01 microseconds. So time 0.01 microseconds. A microsecond is 10 to the minus 6, so that's 1 by 10 to the minus 8 seconds. So that's how long it lasts. It sends out a burst of waves, like so, and that lasts 1 by 10 to the minus 8 seconds. How many complete waves are sent out? We're told that the speed is 3 by 10 to the 8 meters per second, and we're looking to see how many waves are going to be sent out. Right, so we have the speed and we have the time. So we can see what distance is travelled. So from the point where we start the switch the light on, how far will it travel, and then we switch the light off. So what's going to happen is we switch the light on, that light's going to travel a certain amount of time, a distance in that time, and then the light's switched off. So it's what distance has it travelled in that time, and distance is equal to velocity times time, so that's going to be equal to 3 by 10 to the 8 multiplied by 1 by 10 to the minus 8, so 3 meters. So the pulse width is 3 meters. We know that one wave is 6 by 10 to the minus 7 meters, therefore the number of waves is equal to 3 divided by 6 to the minus 7. Put that into the calculator, I get 5 by 10 to the 6 waves. Answer A. Okay, question 20. Here we have a wave shown. We've got a displacement distance. So this is showing a snapshot of a wave. It shows at a particular instant the variation in displacement of the particles in a transverse progressive water wave of a wavelength 4 centimeters. It's traveling, so that's 4 by 10 to the minus 2 meters. It's traveling from left to right in that direction. Which one of the following statements is not true? So which one is false? So the first one, it says from P to S is 3 centimeters. So that makes up That's 1 full wavelength. So this is 3/4 of a wavelength. So PS is equal to 3/4 of 4 centimeters, which equals 3 centimeters. So that is true. The particle velocity at Q is a maximum. Now, what this is saying is it's not wave speed. This is not about wave speed. This is about how quickly that part of the wave is moving. So what's going to happen an instant later is this is going to move up. So we're going to look at how fast it's moving in this direction. So if you think about what happens here is as it moves up, it reaches a maximum, it stops moving up, it gradually gets slower and slower, reaches the maximum, and then starts moving down until again it reaches maximum at the other end and its velocity goes back to 0 because then it's going to move in the other direction. So the fastest point is in the center here. So this is true. This is the quickest speed that the particle has oscillating in the vertical direction when it's passing the equilibrium point. The third one says the particle at S is moving downwards. Well, we can see that as the wave moves this way, this point here, looking at the wave to the left, yes, that is moving downwards. And then finally, particles at points P and R in phase. This is pi over 2. This is 3 pi over 2. They're definitely not in phase. So which is not true? The answer is D. Question 21. It says the audible range of a girl's hearing is 30 Hz to 16,500 Hz. Speed of sound is 330, which is the shortest wavelength of sound. So speed is equal to 330 meters per second, and the speed is equal to frequency times wavelength. So as we increase the frequency, we want to reduce the wavelength of sound. So I'm looking to try and get the shortest wavelength, so the minimum wavelength, when I've got the maximum frequency. Okay, so I'm going to be using the 16,500 Hertz. And remember the wavelength, then the minimum wavelength is equal to speed divided by frequency. So that's going to be 330 divided by 16,500 to get an answer in meters. So it's not this one, not this one, it's this one. So 21, answer C. Question 22. Which of the following types of wave cannot be polarized? Remember, this is asking once again, which is longitudinal? This is EM, so it's transverse, transverse, and transverse. They're all electromagnetic waves. This is a type of sound wave, so this is the one that's longitudinal and hence can't be polarized. So it's answer D. Question 23. A uniform wire fixed at both ends is vibrating in its fundamental modes. Which of the following statements is not correct for all the vibrating particles? So here we have this type of vibration. So, and we're looking for a statement that's not correct. Now, remember, between two nodes, all the particles move in phase. So they're all going to be moving downwards, and then sometime later, they're all going to be moving upwards. So this is true. They vibrate with the same amplitude. Well, this is clearly not true because this point has got an amplitude of 0, and this has got a large amplitude. So that's not true. They vibrate with the same frequency. That is true because when this one goes from its amplitude, its maximum displacement, through the equilibrium to its maximum displacement here and back to the equilibrium, this one will have done the same oscillation. So they have the same number of complete oscillations or complete wave cycles per second, so they have the same frequency. And they vibrate at right angles to the wire. Well, that's clearly true. These are transverse. So the answer for 23, the statement that's not true, is B. Then question 24. A wave motion has period T, frequency F, wavelength lambda, and speed V. Which one of the following equations is incorrect? So we have, well, we know that the frequency is equal to 1 over the period. So we could rearrange that to say that 1 is equal to the period multiplied by the frequency. So that one is true. And remember, we're looking for the statement that's incorrect. Second one, it says that period is equal to velocity divided by wavelength. Well, speed is equal to frequency times wavelength, which gives me that the frequency is equal to speed divided by wavelength, which means that period, which is equal to 1 over f, is going to be equal to 1 over speed divided by wavelength. So that gives me, that should be lambda divided by v. So that looks to be incorrect. What about this one? We've got wavelength equals velocity divided by frequency. Well, that's true. If I rearrange this equation, that's what I get. And the final statement says period times velocity equals wavelength. So we have speed is equal to frequency times excuse me, it's frequency times wavelength, which means that wavelength is equal to speed divided by frequency. And then I can rewrite that as wavelength is equal to speed times 1 over frequency. So wavelength is equal to t times the speed. So that one is true. So the answer, the only one that's incorrect, is B, 24. Now, in an exam, in an exam where you have multiple choice questions, it's all about doing things quickly and precisely. In this case, as soon as I found B, I would mark B as my answer. If I have time later at the end of the exam to come back and check, I would do that. But I would stop there at that point, mark that one, and then move on to the next question. Okay, question 25. This says the diagram above shows a stationary wave and a stretched string, at time t equals 0. Which one of the diagrams A to D correctly shows the position of the string at time t equals 0.01 seconds? Now, why this time? Well, we've got the frequency of vibration. So the frequency of vibration is 50 hertz, which means that the period of vibration, which is 1 over 50, is equal to 0.02 seconds. Now, what that means is that if it's at this position, if a particle is at the maximum position at time t equals 0, that means at time t equals 0.005 seconds, it's got back to the equilibrium position. Then at time 0.01 second, it's at the maximum displacement in the other direction. And then at time t equals 0.015, it's back in equilibrium position. And finally, t equals 0.02, it's back at the maximum positive displacement or amplitude. So these are the stages in that oscillation. So 0.01, that's equal to half an oscillation. So which one of these is going to be? Well, what that's saying is that any points that were at the maximum positive displacement or the positive amplitude, those will end up being at the negative, and the vice versa. So I'm just going to sketch what that's going to look like. So I believe this is going to look like this, and I'm going to try and match this now to one of the pictures. Not that one, not that one. Yes, that one, not that one. So my answer is C. And that's the, oh, no, beg your pardon. Thought that was the end of the paper. I have some more questions. So question 26. A progressive wave in a stretched string has a speed of 20 meters seconds to the -1. Frequency is 100 hertz. What's the phase difference between 2 points 25 millimeters apart? So that's 2.5 by 10 to the -2 meters. Now, I'm going to start by looking for the wavelengths. Remember, I'm looking for the phase difference, so 2 pi phase difference would be one wavelength. So we've got V is equal to frequency times wavelength, which gives me wavelength is equal to speed divided by frequency. Wavelength is equal to 20 divided by 100, which gives me the wavelength is equal to 0.2 meters. Now, we're looking for a distance of 0.25, so, 2.5 by 10 to the minus 2 meters. Therefore, the fraction of a wavelength is, one wavelength is 0.2, so I'm going to have 2.5 times 10 to the minus 2 divided by 0.2 wavelengths. That's how much the distance is between those points. So the distance between the points is an eighth of a wavelength. So that's equal to an eighth of a wavelength. Now, one wavelength is equal to 2 pi radians. Therefore, 0.125, or an eighth of a wavelength, is equal to a quarter pi over 4. So the answer is B. By the way, you'll notice that I'm going very quickly through these in the sense that once I've done an answer, I'm going straight to the next one. This is also something that you need to do when you're doing multiple choice questions. You can't wait and say, okay, I've done quite well on that one, and then take a little break. You have to go very quickly between the questions, as generally speaking, you don't have much time. So which one of the following statements about stationary waves is true? So remember, stationary wave, and I constantly draw these little diagrams just to help my thought process. So here are my nodes, these are my antinodes. I know all of these points between the nodes are in phase, and I know that the amplitude varies. It's here it's 0, here it's maximum. So what do they say? We're looking for a statement that's true. Particles between adjacent nodes all have the same amplitude. Well, that's clearly false, because the amplitude of this one is not the same as this one. That's false. Particles between adjacent nodes are out of phase. All the particles between these two nodes are in phase. If these are moving down, then these ones are moving up. So that one is not true. Particles immediately on either side of a node are moving in opposite direction. That is true. So if this one's moving down, this one's moving up. So that's true. There is a minimum disturbance of the medium at an antinode. No, it's the opposite. The minimum disturbance at the node, maximum disturbance at an antinode. So that's not true. So my answer is C. Then question 28. Which one of the following types of waves cannot be polarized? Again, this is simply saying which one of these is a longitudinal, or in other words, a sound wave. This is EM, this is EM, this is EM. Answer B. You can see that question has come up several times in exams. These are all exam questions. Then we have the least distance between 2 points of progressive transverse wave. The phase difference is pi over 3, and the actual distance is 0.05 meters. So the distance is equal to 0.05 meters. The frequency is 500 hertz. We want to know what is the speed, so we need to know what is the wavelength. Well, 2 pi is one wavelength, therefore pi over 3 is a sixth of a wavelength. So this distance is equal to a sixth of a wavelength. Therefore, the wavelength is equal to 6 multiplied by 0.05, which equals 0.3 meters. Okay, and now I can use my equation. Speed is equal to frequency times wavelength. So that's 500 multiplied by 0.3 equals 150 meters per second. Answer C. Question 30. Which one of the following statements about stationary waves is true? Particles between adjacent nodes all have the same amplitude. That is false. Particles between adjacent nodes are out of phase with each other. That is true. Particles immediately on either side, particles between adjacent nodes, so that's between this node and this node. No, those are not out of phase. Those are in phase because they're all moving in sync, so that's false. Particles immediately on either side, if this one's moving up, this one's moving down, that's true. Minimum disturbance at an antinode, that's false, it's the maximum. So again, it's the same question as came up obviously in a previous exam. The answer is C. Then we have, yes, the last question. Two waves with amplitudes alpha and 3 alpha, or no, is it A? It's A and 3A interfere. The ratio amplitude and interference maximum, amplitude and interference minimum is. So what they're saying is we've got one wave is like this, another wave is like this. This has got an amplitude of A, its amplitude is 3A. So for constructive interference, we're doing a vector sum. So therefore the maximum is equal to 4A. The minimum is where we have this one is A and the other one is in antiphase, so it's minus 3A, so that gives me minus 2A. So the ratio is going to be 4A over 2A. The sign doesn't really matter, we're just looking at the ratio of the value for the amplitude, so that's going to be 2.